afternoon and welcome to Cálam Cymru sessions. This session will focus on physics, year 11, stars and the universe, and will be presented by Mr. Rydd from Cynbeg School in Bridgend. The session will last around 45 minutes, where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section, and we will endeavour to answer your question during the session. The session will be recorded and the recording with any relevant resources uploaded to the e-sgol website in the Cálam Cymru area. Thank you very much, Mr. Rydd.
Okay, thank you, Mrs. Owen. Hi and welcome to this session on stars and the universe. In this session, I will be covering the life cycle of stars, plus HR diagrams, which is higher tier content on double award. And then in addition to that, we will be looking at absorption and emission spectra. We'll be looking at the evolution of the universe as well, which is, if you are sitting triple science, or if you like the individual physics GCSE content relevant for that course. So there's a bit of a mix in here. I should also mention as well that other parts of the stars and planets syllabus that are required for double award science have been previously covered in a video which I did last year. So please go on if you want to have a look at that because there's additional content there. Right, so straight into the evolution of stars then. What do we need to make a star? Well, quite simply, we need a star-forming nebula. Now, what is that? Well, it's a giant cloud of dust and gas. That's all you need to make a star. Here is an example of such a nebula, or such a star-forming nebula. This is a very famous star-forming nebula. It's called the Pillars of Creation, and it was first photographed by the Hubble Space Telescope. Here's a zoomed up image, or zoomed in image rather, of the Pillars of Creation. And it's a very, very interesting nebula because within there we have stars being born. It's also known as a stellar nursery. And essentially, all you need is gravity, dust and gas, and a long period of time for that gravity to pull that dust and gas together into a really, really hot ball of gas. Now, that hot ball of gas we call a protostar. And here's an example of a protostar, or a star being born. And you can see in this image here, essentially what you've got is a hot ball of gas. Now, shortly after that, the pressure and the force of gravity will cause the particles, the hydrogen nuclei in that gas, to collide with such velocity that the star begins to undergo a process known as nuclear fusion. Nuclear fusion is where lighter elements combine to form heavier elements, and in doing so release a massive amount of energy. This energy then is what really ultimately we get as sunlight, if you like. It is the process by which stars generate the energy and shine. So once that happens, once a star has collapsed into that ball of hot gas and nuclear fusion has begun, we say that a star is born at this point, and it becomes what we refer to as a main sequence star. Now, this is true of smaller stars like our sun, or even larger stars, massive stars, if you like. They both undergo this same initial process. It is the same for both. The only difference is you'll notice here that main sequence massive stars are in fact more bluish in their color, whereas Sunlike stars may be yellowish and in some cases more orange-like. So a main sequence star will stay as that for a very long time, and it will be stable. Now, the reason why it is stable is because of the action of two forces. You have still got the force of gravity, which is pulling the star together, but due to nuclear fusion, we've also got an outward force, which is pushing the star out. Now this force, sorry, is called radiation pressure. And as I said, we've got gravity pulling inwards. Now, from Newton's first law, you should recall that if two forces are balanced or equal and opposite, then an object will remain stationary, and we can apply that law here. If these two forces are balanced, then the star will remain, if you like, at a stable radius. It will stay as it is, and this will continue for a long time. Now, in the case of a star like the Sun, it will remain like it is for another 4.5 billion years, and in fact, it's already been a main sequence star for 4.5 billion years. The lifespan of the Sun is around 10 billion years. So we can look at the Sun and think of it as a bit like, well, middle-aged in a way, but like Sir, I suppose. No, I still think I'm on the younger side of things. Anyway, so here now I've just broken down, right, those stages, and I have bullet pointed them for you. So you can go back and pause the video. I've discussed this already. You can go back and pause the video and make your own notes if you like. But so far, were you to be asked to describe the evolution of a Sun-like star, you wouldn't go far wrong if you made these notes. Okay, so moving on. What happens then when a star comes to the end of the main sequence, or the main part of its life? Well, it's all to do with the forces again in the center of that star. When a star runs out of hydrogen, it's only got so much hydrogen to fuse. Eventually that core of the star will run out of hydrogen and it will start to fuse together heavier elements. When this happens, even more energy is generated, and that radiation pressure that I mentioned earlier on, it starts to exceed, it starts to overcome the gravitational force. It becomes larger than the gravitational force, causing the star to expand. Now again, this is true for Sun-like stars and massive stars. So that's what I've shown on this diagram. It is true for Sun-like stars and massive stars, the same process. It starts to fuse together heavier elements, it causes it to swell, causes it to expand because that radiation pressure starts to overcome and overwhelm the gravitational force. And expand it will do, significantly so. So, for example, when the Sun comes to the end of its life, it will swell to a size that will likely engulf not just Mercury, not just Venus, but also Earth, possibly even Mars. So it will become a red giant so big, that star will become so big that small yellow ball that you see in the sky will one day become this enormous red monster that will devour the Earth. Good times. But hey, like we said, it's not going to happen for another 4.5 billion years, so don't worry about it. Now, a red giant then is what we call, if you like, that sort of route for a Sun-like star. If it's a massive star, it forms a red supergiant, which is its own category again, but essentially much the same thing. If you wanted to see a red giant, you're not going to notice it as a red giant, but if you know anything about constellations, this is the constellation of Orion. So if you get a little app on your phone, you can look it up. And in fact, this star here, Betelgeuse or Betelgeuse, is in fact a red giant. All right, and you know, cosmologists watch this star very closely, and I promise you, if you look at this star in the constellation of Orion, you will convince yourself that that star is a little bit pinkish, a little bit reddish compared to the others. Certainly, of course, compared to Rigel, which is a very hot blue star. Anyway, moving on. What will happen to a Sun-like star then after its red giant phase? Well, we said that it expands, and it will continue to expand, in fact, and those outer layers of the star will drift off into space, forming what we call a planetary nebula. And here are a couple of my favorite planetary nebulas. Nebulae, nebula, nebulae. So you can see here the outer layers drifting off into space, and at the center, look, you'll observe a little white dot. Now, some of the sharper ones amongst you I know will be able to tell us what that white dot is. It is, in fact, the end point of a smaller star like our Sun. It is, in fact, a white dwarf. Okay. Well done if you knew that. Yeah, now the white dwarf is just the white hot remaining core of the star. Now the outer layers will drift off into space, and amazingly these outer layers might go on to in fact cause other stars to form. Isn't that nice? And on it goes. Right, here's another planetary nebula. You can see here that that white dwarf has cooled now, and it is a red dwarf. Great television series, you wouldn't know. For your time. And then here's another one. I could go on all day, but I'll leave it be. Okay, so there is your description then of the life cycle of a Sunlike star. All right, pause it, make some notes if you need to. What about a larger star? What about a massive star then? Well, again, like we said, the red giant phase is still there. But now, whereas before those outer layers drift off into space, now the star has enough mass and therefore enough gravity to pull those outer layers back in towards the core. And then as they accelerate, as they get faster, they collide with the core of those outer layers, and they produce the most energetic event that we're aware of in the universe, what we call a supernova. All right. Here's a picture of a supernova. This galaxy here is Andromeda, which is our nearest neighboring galaxy. And here, this event here is a supernova. And believe it or not, just prior to this image being taken, that bright white light wasn't there. That star, of that bright light that wasn't in the image at all. That's because it hadn't exploded yet, and astronomers picked this up shortly afterwards. Okay, and that, believe it or not, that supernova was so bright it virtually outshone the whole of the galaxy temporarily. Here is the Crab Nebula, which is the remnants of a supernova. It looks like the aftermath of an explosion. I think you'll agree. And here's another one. That's kind of cool. And another one. Anyway, pause those if you want to have a look at them. Now, after that, then, endpoints. Well, that core after the supernova event, which again, you know, the remnants of can go on to form other stars, okay, because they will form other nebula. But the core that's left, okay, can form what we call a neutron star. I'm not going into exactly what a neutron star is, but they were discovered in part by Jocelyn Bell Burnell, who is a very, very famous astrophysicist and cosmologist for discovering what we call pulsars. And pulsars led to our sort of understanding of neutron stars as well. So an incredible discovery there, an incredible lady as well, actually. So neutron stars, one endpoint, extremely dense, okay? The core collapses down. The entirety of a star will collapse down to an object which might be something like 15 to 20 kilometers wide, which isn't big, is it? Okay, think how big a star is, but it'll still contain, you know, most of the mass. So these things are massive yet small. So it's something you can wrap your head around that. Something can be massive but small. Yeah, it's true. It's true. And you know, it's so dense, in fact, that a teaspoon of that stuff would weigh about as much as Mount Everest. I'm not making it up. It's just true stuff. But what if a star is even bigger, sort of, you know, 8-9 solar masses? Well, the core now is so dense, it has so much gravity that the core collapses and it forms what we call a black hole. It's difficult to describe what a black hole is. I mean, we could talk about it for a long time, more time than, you know, it take more time than I've got in this video. But suffice to say that all of that mass collapses down into a volume which is non-existent. We call this a singularity. So all of the volume, all of the mass of a star collapse down into something that has no volume. That's why physicists are so interested in studying them. Now this is an image of a black hole. It's an artist's impression of what a black hole would look like were it to be feeding on a star. And they do feed on stars. How sinister does that sound? We call this an accretion disk, and we've got these huge jets that are emitted, okay? And this is what an artist has assumed it might look like, okay? A year is one such jet that we've imaged, all right? We're in a distant galaxy. That jet caused by an active or feeding black hole. And in 2017, this image was taken. Pretty incredible feat of astronomy, imaging a black hole. There you can see the absence of light in the center. So another point just worth mentioning, we've gone looking for black holes, and we found one at the center of the Milky Way, which is pretty awesome. And in fact, we found one in the center of Andromeda. We found one in the center of Andromeda first, to be truthful. And then we found one in the center of our own galaxy and at the center of other galaxies. And it seems as though it could be the case. Some people have argued that a black hole is necessary for galaxy formation, which is kind of interesting. I'm not going to show you that video now. Right. So this is the life cycle of massive stars. Then again, pause the video, make the notes if you would like. To. Right. Moving on now. The other thing to remember is that the material that's ejected in the supernova events, all those heavy elements, and I should mention as well that the heaviest elements, I forgot to say, the heaviest elements are created in those supernova events. So everything heavier than iron, okay, is created only in a supernova event. So the very fact that we've got uranium, gold, like heavy elements on Earth, the very fact that we've got these elements on Earth means that the Earth and our solar system is formed out of the remnants of a supernova event. So I can tell you at least that you are made of stardust. So that's kind of nice. Right, some past bit questions then. Let's go quick. Right then, so you've got to match these up now. So we have got stage 1, stage 2, stage 3, and then the final stage, and we've got to put these in order. So which comes first? Let's see. Red supergiant, supernova, black hole, so main sequence stars, number 1. The next stage is, well done, yeah. Red supergiant. And then the next one, supernova, stage 3, black hole, stage 4. Simples, okay? So just learn your different stages of the life cycle of stars, and there's a very good chance you might get an easy question in the exam to pick up some easy marks. Oh, interesting. Looks like a good one, doesn't it? So we've got to here name the force that's present in a main sequence star that balances the weight, and I think we can do that because we've got gravitational force inwards and we've got radiation pressure outwards. Okay. Oh. We're written down there. Radiation pressure outwards. Nice. Moving on. Choose the words from the box. Okay. This is something worth reading. Mind, right? I pulled up a few of my students the other day for making this mistake. Because sometimes you go, yeah, I know I'm going to put the words in the boxes, and yeah, it's fine. All right. But read the question carefully, because look what it says here. Each word may be used once, more than once, or not at all. Now that makes a difference, because sometimes you might be thinking, well, I've already used that word, I can't use it again. But the question is explicitly telling you that you might need to use it again. So main sequence stars generate energy by nuclear fission or fusion. Which one was it? Good, well done. Fusion. Think about fusion. Fusion is coming together, joining. So it's lighter elements joining together, like hydrogen joining together to form helium. So yeah, of hydrogen into helium. By the way, nuclear fission is the splitting. Think of fissure, splitting. That's the splitting of elements. Then we use that nuclear energy, for example, in power stations. Heavier elements created when stars much larger than our sun collapse. These heavy elements include, well, I mentioned one earlier on, uranium, which is the heaviest naturally occurring element that we have. If we use in fission reactors on Earth, we only have elements heavier than iron. right? Because they're created during a supernova explosion. Good job, well done. So I'm going to say that we've covered the life cycle of stars, why stars are stable, and then the return of material, including heavy elements, into space during the final stages of the life cycle of giant stars. So, you know, when a star goes supernova, those heavy elements are returned into space where they can go on and become a part of other solar systems. The origin of the solar system from the collapse of a cloud of dust and gas, including elements ejected in a supernova. We're going to say that we've that as well. Right, we're on to now higher tier content. And if you, but I think this is certainly something that is appropriate for even foundation students to have a look at, because it's only going to reinforce what we already know about the evolution of stars. So the Hertz-Sprung-Russell diagram is a diagram that was put forward as a way of categorizing stars and looking at stellar evolution. Here's one such diagram. I've got a better one on the next page, and I'll talk you through it. So on the diagram, you'll notice we've got the color of stars along the top here, the spectral class, as it's sometimes known. We've got temperature as well. So you can see a relation here as well between temperature, look, and color. You can see the red stars are cooler, and you can see that the blue stars are much, much hotter. You can even see the position of our own sun there. As well, we've got something called absolute magnitude, which in your exams actually be written as brightness. So don't worry about that. It'll be written as brightness in your exams. So you've got the brightness of the stars as well on this axis. And you can see here, it kind of makes sense, doesn't it, that, you know, if you take two main sequence stars, two stars on the main sequence, this one, speaker, or, yeah, is that what you say? Not sure. This one, anyway, this blue star is, look, brighter, okay? It's brighter than the sun. And in fact, it's hotter than the sun, all right? And it's bluer, and the sun's in fact yellow, isn't it? All right, so we can take plenty of information from here. As well, up here, we've got our red giants and our red supergiants. So what we can say about the red supergiants and the red giants is that they are cooler. Look, if you look here, in terms of temperature, they're cooler, they're redder, but they are still, this is interesting, they are still very bright. Right? They're still very bright, much, much brighter than the sun, much, much brighter than a lot of stars in the main sequence, and that's because they are so big. Their size makes them, you know, they produce a lot of light, even though they might be a little bit cooler. Okay, right, anyway, moving on, we'll have a look at the past paper question. Use the information in the diagram to answer the following questions. Estimate the surface temperature of our sun. So we've got a HR diagram here. Our sun is here, and all we've got to do is just, you know, do one of the dotted lines. Now I'm going to say that's somewhere between 5,000 and 7,000. We call it 6,000 K. K stands for Kelvin. Okay. It's a different temperature scale that we use in physics and in science, named after Lord Kelvin, of course, and the amazing work he did in determining absolute zero. But that's for another time. So next, state two differences in the properties of Alpha Centauri B compared with our sun. Well, Alpha Centauri B is here, and the sun is here. So what two things can we say? Two differences, it says. Two differences can we put down? Well, it's cooler. That'd be one, wouldn't it? And what else can we say? It's smaller. If you look at this axis here, look, we've got large, we've got small here, okay? And we could have even said a third, we even could have said dimmer. So any of those, sorry, that handwriting is terrible, but you get what I'm saying, you know, it's dimmer as well. So any of those would be fine. State one way, our sun and Alpha Centauri B are similar. How are they similar? They are both, look, they are both on what we call the main sequence, okay? Both main sequence stars. Nice. what changes will happen in the sun to cause it to expand to a red giant. So it could talk a lot here. It's an awkward thing for 1 mark, right? But what we'll say is it runs out of, what gas was it in the core? Runs out of hydrogen in core, fuses heavier elements. Use information from the diagram to describe the effect these changes will have on the properties of the sun. Well, if the sun becomes a red giant, how will its properties change? Well, it will kind of go up here, look, right? It heads this way. And if it becomes a red giant, it's going to be brighter and cooler, right? I'm not going to write this all because I just want to get through as much stuff as possible. But if you're in your exam, I expect you to use full sentences there, right? And not just to rush through it. Mark the diagram with an X to show where our sun will end its life. The sun will end up as a white dwarf, so we'll end up down here somewhere, anywhere in this region. Okay, great stuff. All right, so I'm going to say that we've done that. I'm going to say, well, we've already covered these, haven't we? And we're going to say that we've covered HR diagrams as well. On to absorption and emission spectra. And at this point now, we have hit triple science, or we've hit the content which is explicitly for students who are just studying the GCSE single standalone in physics. Okay, I put this slide here, and it's quite a famous image actually, mostly because Pink Floyd uses it as an album cover, Dark Side of the Moon. But what it does show is it shows how white light or light can be split up into different colors, which is very important for this next bit, because we can actually turn this light source into a continuous spectrum. We can see all of the different colors and all of the different wavelengths of light. So the next thing we're going to look at, right, are absorption and emission spectra. So when we have, I don't know, a light source, let's say like something simple like a light bulb, okay? It produces light, some red light, some orange light, green light, and all added together to make white light. Okay, that's something like a light bulb. That's something like the sun. However, what we can do as well is we can actually pass energy through a gas. So in this case, this is hydrogen gas, and you can get a tube of hydrogen gas, pass an electrical current through it, and bam, it's going to produce some light. Now the light it produces is quite different. It produces what we call an emission spectra, and it produces very specific wavelengths of light. Now they correspond to electrons jumping around in atoms. Right? We're not going to go into that in too much detail now, something for A level maybe. But these very specific wavelengths are absolutely characteristic and only found in hydrogen atoms, which is really important. So this emission spectra is a bit like a fingerprint for hydrogen, right? So that's what happens if we pass an electrical current through a gas and excite it. But we can also produce what we call an absorption spectra. Now, what's an absorption spectra? Well, if we take a source like the sun, and well, I'll show you on the next slide actually. If we take a light source like the sun, which produces a continuous spectrum from the interior, then the atmosphere of the sun, which contains gases and different elements, won't just emit those wavelengths, but it also absorbs those wavelengths. Okay, so if you notice here that the absorption spectra perfectly mirrors, right? So this absorption spectra here, it perfectly mirrors the emission spectra. And it's also the case that, yes, hydrogen gas, for example, can emit specific wavelengths of light, but it will also, and crucially, absorb very specific wavelengths of light. So what that means is, if we've got hydrogen gas in the atmosphere of a star, then it will absorb those specific wavelengths, which we can see here. And when they arrive to us at Earth, then, when we look at them through a telescope, or we pass them through a prism, what we'll see is this absorption spectrum. And what this can tell us, well, it can tell us a huge amount of stuff, right? First of all, it can tell us what elements are present. Remember, I just said that hydrogen has its own characteristic emission spectra, so we can tell exactly whether there's any hydrogen in the atmosphere of the star, which inevitably there will be. But we can also tell just how much hydrogen there is there by the strength of those lines. We can also tell as well if there are any other elements present. And from those other elements, we can actually determine whether or not it's a first generation star, a second generation star, how old it is even. Right? Cosmological redshift. Right, what's this? Well, let's imagine this is my my hydrogen spectrum. Okay. If I have a star which is moving away from me, then what that will mean is that the spectrum is moved ever so slightly. It's shifted towards the red end. This is something called the Doppler effect. And the Doppler effect occurs when a wave source, in this case a star, is either moving towards us or away from us. The effect of a wave source moving towards us or away from us is to either compress, squash the wavelength and shorten the wavelength, or lengthen the wavelength somewhat, okay? And depending on how much these lines here have shifted, if you look here, you can see that this line here has shifted. Depending on how much this wavelength has changed, that will, the proportion by which is changed will determine how fast that object is moving, or that star is moving. We observe it with light, we observe it with sound. It's a wave phenomenon. So here's the thing. If we go hunting for hydrogen lines in stars, in other galaxies, then what we're able to do is work out by how much those hydrogen lines have moved in the absorption spectrum, we're able to work out just how fast they go in. So not only can we determine the composition of stars, how old they are, but we're able to also figure out which direction they're moving and how fast. Now, if a star's moving towards us, it'll be blue shifted. If a star's moving away from us, it'll be red shifted. If a galaxy is moving towards us, again, it'll be blue shifted. The wavelengths will be slightly shorter. If a galaxy is moving away from us, it will be red shifted. And that's what we can see in this little infographic here. We can see a galaxy moving or stationary with respect to Earth. That's this one here. We could see what happened if a galaxy was moving away from us. See this line here. Okay, this line here has moved towards the red end of the spectrum, and were a galaxy to be moving towards us, then this line again is moved now towards the blue end of the spectrum. So on to Edwin Hubble now. Edwin Hubble was a great astronomer, made one of the most staggering discoveries that any human being has ever made, knew before anyone else the age of the universe, which absolutely blows my mind. He made a hypothesis based on the physics that we've just talked about, the idea that galaxies will have either a red shift or a blue shift, depending on whether they are moving towards us or away from us. He made a simple hypothesis, and he said that he reckoned some would be moving towards us, some would be moving away from us, a bit random, a bit like, I guess, gas particles in a container. So he thought maybe some will be coming this way, some will be going that way, maybe this guy down here, that one like this, oof, look at this guy here. He thought it'd be random distribution. Now, what he actually found, though, he was really surprised by. What he found was that galaxies were, in fact, all red-shifted. That's the first observation. The second observation was that most of the distant galaxies have the largest redshift, which was, again, a bit of a surprise. And the conclusions he drew were quite staggering. Firstly, galaxies to be moving away, the universe must be expanding. If I got a group of people together in the schoolyard and I said, I give them one instruction, you all need to get further away from each other, that group of people would spread out. So the universe, by the same logic, must be expanding. That's the first thing. Awesome. Second thing, what that means is that the universe was smaller yesterday, it was smaller the day before, 1 million years ago it was a lot smaller, 1 billion years ago it was a hell of a lot smaller, but at some point it would have been all in one place, which is a staggering idea. Just like the shards of shrapnel that a grenade might throw out. At some point, if you wind the clock back, okay, all those pieces of metal would have come from one point, all right? And we call that single point the Big Bang, all right? And that's the start of the universe. It was later known as the Big Bang. And then finally, the universe is accelerating its expansion. And this is probably one of the most amazing findings from all this, is that the most distant galaxies, like this guy up here, is actually showing us the biggest redshift, which is actually meaning that it's moving faster than the other galaxies, which means that the universe is accelerating its expansion. It's not just expanding, but it's expanding at an ever-increasing rate, which was just an incredible discovery. Okay. I'm going to just talk quickly about cosmic microwave background radiation then, okay? So cosmic microwave background radiation is essentially a wavelength of radiation that we detect with our telescopes all the time, regardless of where we point in our telescopes. Initially, when this was discovered, it was thought that the telescopes must have been faulty or something must have been wrong with them, must have been broken. But it was later discovered and confirmed by others that this radiation was everywhere. And what it was then subsequently thought to have been, and what we realized it was, is that it's the radiation left over from the Big Bang. So that Big Bang that we just mentioned, that huge explosion, the radiation that was created in that moment, really high energy radiation, due to the expansion of space, because space stretched out, it stretched out the wavelengths of light, and what is left is like the afterglow of that explosion, right? So you're seeing what that explosion looked like many years later in the cosmic microwave background radiation. The only explanation for the presence of that radiation is from a single event, really, which we call the Big Bang, or that explosion. All right. Let's do some questions then. So first of all, it says here, an absorption spectrum from a star is a pattern of black lines on a colored background. Boxes in the left column list 4 features of the spectrum. The boxes in the right column list the causes of these features. So draw a line from each feature to its correct use on the right. So a single black line is due to one wavelength of light being absorbed. Black lines move towards the red end of the spectrum, or well, they do that because of cosmological red shift. So the black lines move towards the red end of the spectrum if we've got a red shift. A pattern of black lines, well, these pattern of black lines, they tell us about the elements in the star, and by comparing those black lines and the positions of them in the spectrum with an emission spectrum, we can figure out just what elements are in that star. And then finally, a colored background, well, that's due to the wavelengths of visible light emitted by the star. The star emits a continuous spectrum, and then the absorption spectrum sort of takes wavelengths out of it. The nearest star to our solar system is called Proxima Centauri and is about 4 light years away. State what the term 4 light years means. Well, this is sort of a bit of a revision really, but it means 4 light years is a distance. It's the, if you like, it's the distance light, or if you like, let's say it this way, light has traveled for 4 years, okay, to get to Earth. Get something wrong with my pen, I do apologize, to Earth. Sorry, bad time. So light travels for 4 years to get to Earth, okay, and it's the distance light travels in that time. All right, it's the distance light will have traveled to get to Earth. Okay. The spectrum of light coming from galaxies is crossed with dark lines. Explain how the dark lines arise in the spectrum and outline the information that they give about those galaxies. Well, let's just talk about this one quickly then. All right. So the dark lines indicate the elements present in star, and they can also as well, okay, we can, that by comparing, this is known by comparing to emission spectra from elements. And they could also tell us, okay, if lines are shifted, they would tell us the redshift and if they told us the redshift, the velocity of the as a star or galaxy, sorry, galaxy. All right, that's 3 good points for now. I think I want to move on to another couple of questions if possible before the end. So if we've got something that's 20 million light years away, the time taken for the star to get to us is obviously 20 million years. Nothing hard about that. Here we've got light from the inner part of a star shining through gas atoms in the outer cooler atmosphere of the star, and then we've got light leaving the atmosphere. All right, let's see if we can do a question on this out quick. So so we've got 3 diagrams, diagram A, B, and C. Put the correct column below, put a tick in the correct column below to show which is the correct diagram for each statement. So, light leaving the atmosphere of a star. Which one's that going to be? Well, the light leaving the atmosphere of the star is going to be given by, let's see now, the absorption spectra. That's going to be B, all right, because the atmosphere will absorb certain wavelengths of light. And then the light from the inner part of the star, well, that would have been prior to, look, it would have been prior to any absorption by the atmosphere. So that would have been that one, okay? The spectrum below is from another star in the same galaxy. Explain how the line shows that the stars are different. So we could say different absorption spectrum we can say that stars contain different elements. All right, stars contain different elements, okay? And then state what happens. Says line spectrum distant galaxies are shifted towards the red end of the spectrum. State what has happened to the wavelength of those lines. Well, the wavelengths are longer. And then finally, the lines in spectra from some other galaxies are further redshifted. State what this tells us about those galaxies. Remember, bigger redshift, they are further away. I've got to go now, guys. I hope that this has been helpful. I hope that you learned plenty about stars and the universe, and especially that higher tier content as well. I'm going to have to go now, and I'll maybe see you again.